We'll have assigned 8C number 7. A 2.10 kilogram block resting on a frictionless horizontal surface is attached to a spring whose force constant is 83.8 newtons per meters as in the figure below. A horizontal force F causes the spring to stretch a distance of 4.57 centimeters from its equilibrium position. Alright, so this is a diagram the problem gives us. It tells us that this is a block of mass 0.210 kilograms. The spring constant is 83.8 newtons per meters, and that a force causes a maximum displacement of 0.0457 meters. So part A asks us to find the magnitude of the force that causes that displacement. So the equation we're going to use here is that K is equal to F over X. This is effectively what the measure of a spring constant is. It's how much force is required per unit distance. Plugging our known values of 83.8 newtons per meters for the spring constant and 0.0457 meters for the delta x gives us this, and now we just got to multiply both sides by 0.0457 meters. This gives us a force of 3.83 newtons. Part B asks us to find the maximum potential energy in the system. Denoted here as U max, it's equal to 1/2 K times the amplitude squared. Plugging our known values of 83.8 newtons per meters for the spring constant. And here the amplitude is going to be the period of max displacement from the equilibrium. So it's going to be 0.0457 meters. Plugging this all into a calculator yields 0.0875 joules. Part C asks us to find the magnitude of the acceleration right after it hits the equilibrium point. So this is going to be the maximum acceleration. Our equation for this is that the maximum acceleration is equal to the amplitude times omega squared. And we all know that omega is just the angular frequency. It's 2 pi times the frequency. Now that's great, but we got to determine the frequency. And the frequency is 1 over the period. So know that the period is equal to 2 pi times the square root of m over k. We know that the frequency is equal to 1 over t, and it is therefore equal to 1 over 2 pi square root of m over k. Plugging our known value of 0.210 kilograms for the mass and 83.8 newtons per meter for the spring constant, we get a frequency of 3.18 hertz. Alright, so now we calculated the frequency, we could plug it in to our equation for the maximum acceleration. Substituting in 0.0457 meters for our amplitude, and plugging in 3.18 hertz for our frequency. Multiplying this all out yields an acceleration of 18.2 meters per second squared. And part D asks us to find the maximum velocity of the mass, and this is going to occur at the equilibrium position. And our equation for this that we're going to use is that the maximum potential energy is equal to the maximum kinetic energy, because it's a system without friction. So we already know what the maximum potential energy is, 0.0875 joules. And we know that kinetic energy is just 1/2 mv squared. We know the mass is 0.21 kilograms. So just doing some simple algebra here, we know that the velocity is going to be equal to the square root of 2 times 0.0875 joules all over 0.210 kilograms. Plugging this all in your calculator yields a maximum velocity of 0.913 meters per second. In part G, asks us to find the maximum coefficient of friction that will allow the mass to return to equilibrium from the amplitude. And so the way we're going to quantify this is that the highest coefficient of friction for the mass just to reach the equilibrium point would be when all of the potential energy stored in the spring is converted to thermal energy because of the force of friction. So we're going to have our equation U max is equal to I max, where I is just denoting the internal energy. So we already know the value of the maximum potential energy. And we know that internal energy is equal to the frictional force times the distance. And we know that the force of friction is equal to the normal force times the coefficient of friction. And now we have a problem here. What's the normal force? To solve that, we got to draw our good old-fashioned free body force diagram. So we got 4 forces acting on the mass. We got gravity pulling it down, normal force pushing it up, the spring pulling it in, and the force of friction acting opposite the motion of the spring. So from here, our vertical equation is simply Fn minus Fg is equal to 0. So adding Fg to both sides yields Fn is equal to Fg. But we know Fg is equal to mg, so we know Fn is equal to mg. Plugging this all back in up here, we still have the same 0.0875 joules is equal to mg times the coefficient of static friction times the displacement. Now we're solving for the coefficient of friction, so I'm going to divide by every term that's not the coefficient of friction. Now I'm going to plug in what we know for the variables down here. We know the mass is 0.210 kilograms. We know the gravitational constant is 9.8 newtons per kilogram. And we know the maximum displacement from the amplitude to the equilibrium point is just 0.045 centimeters. Plugging this onto your calculator yields a coefficient of friction of 0.930. When I was first doing this problem, I had problems quantifying the internal energy. I knew it was the force of friction times the displacement, but I did not know how to determine the force of friction. And then I realized that I got to go back to the old days and draw a good old-fashioned free body force diagram to get the normal force, because we know that the force of friction is the normal force times the coefficient of friction. And also I was having problems determining the maximum acceleration of the mass, because I knew that the acceleration is equal to the amplitude times omega squared. I had problems determining what omega was because I thought that omega was the angular velocity, but it's only moving in a straight line. So then I realized that there was a second equation for omega, which is just 2 pi times the frequency. This problem shows my growth because it shows my understanding of an oscillating system, and then I'm able to calculate the maximum acceleration and velocity of an oscillating object. Also, it shows that I did not forget how to determine the energy stored in the spring constant. And all this over here shows that I'm able to use free body force diagrams and energy methods to solve questions. Thank you.